Thank you. So we're going to talk about ordinary least square regression. This is a very important statistical technique because everything that we learn beyond OLS regression, this serves as the foundation, right? This is where it all begins in terms of your analysis of the data. So what is OLS regression? It's a subset of generalized linear models, and there are many generalized linear models. We won't go into them here and now, right? I'll talk a little bit more about them later on. It's the most widely used quantitative technique in education and social science research. So if you're doing quantitative analysis in education, more than likely you're going to be using OLS regression or a technique that builds on OLS regression. It's easy to use and interpret. It includes a single dependent continuous variable. Sometimes in the literature, it's referred to as an outcome. You've heard me use that word. Or endogenous response. I think in psychology, that's the term that's used, right? And it involves the use of independent variables. So in the literature, particularly in economics, predictors, those are the independent variables. Covariates, I think again in psychology, that's also the term. Exogenous in some other literature, or explanatory variables, right? They mean virtually the same thing, right? So there's a history that goes way back with regard to the use of OLS, back to the 19th century, that began in the areas of agriculture and hereditary studies, originally applied to biology and psychology. It's commonly used in the social sciences and education to test hypotheses, so looking at K-12 education, higher education, sociology, and baseball for fun. I've used it just for fun, right? The last thing I looked at, I downloaded this huge database of baseball statistics, and I looked at, well, I wonder how players are paid and what is it that ties their salary? What is it that determines their salary? Particularly players who are position players, with the exception of a pitcher, because it changed, where the pitcher no longer bats unless it's that star from plays for the California team.
I keep seeing news articles about
Shohei.
Shohei Ohtani.
Yes, Shohei Ohtani, yes. He pitches and he bats, but he's the rare exception, So I wanted to see if the salary is based for those hitters, what is it based most on? And it appears as if it's home runs. So there's a strong relationship between the number of home runs that these players hit and their salary. It's a positive relationship, right? So I used it for fun because I'm a baseball fanatic. It's used to forecast and predict. So in economics, it's used to predict, usually wrong. The predictions usually come out wrong. And political science is used to predict elections, and we all know that those predictions also come out wrong for the most part. Determine what variable and factors are important. And I've mentioned this before. What importance in econometrics and statistics, what that means is whether or not the variable is statistically significant. So importance is narrowly defined, right, by statistical significance. So any questions about this? It's just a little history and context. So what is the purpose of OLS regression? It's to explain differences in the dependent variable that may depend on those independent variables that you include in a model. Predict when a specific value of the dependent variable might occur based on the values of the independent variables, right? So that's for prediction. In this class, it's very important that we become familiar with OLS regression. And the other regression methods that we will cover are extensions of OLS regression. So OLS regression analysis involves estimating the form of the relationship between dependent variables and independent variables. So what form does it take? I'll talk a little bit more about that. The direction and strength of association between the dependent and independent variables, and which independent variables are important. Again, narrowly defined, statistically significant, and which are not. Okay? So there are some classical assumptions in OLS regression. You don't have to commit these to memory, but from time to time you may want to revisit this particular slide in this particular session. So the first one is linearity. The regression model is linear in the coefficients and the error term. And we'll talk a little bit more about what that means. Again, you don't have to remember this, but the error term has a population mean of 0. Okay? Homoscedasticity. It took me a while to pronounce that word, right? Yes, it's a tongue twister. The error term has a constant variance. There is no heteroscedasticity, meaning there is no variance in the variance. It's constant, right? That's an assumption of OLS. There is no autocorrelation, or sometimes called serial correlation, meaning there's no systematic pattern to the errors. Observations of the error term are uncorrelated with each other, meaning an error is, say, in time 1, year 1, or year 2 is not related to year 1. Year 3 error is not related to year 2. Year 4 is not related to year 3. Okay? The errors aren't, there's no pattern in the errors, right?
So this tripped me up on this last quiz. So I got 4 and 5 wrong. And 4 seems very similar to what you just mentioned on here. So how are they different?
So tell me what 4 on, because again, I remember, what was 4 on the quiz?
That's what I remember on it.
Oh, yeah, the null hypothesis.
Yes,
H theorem.
the H theorem.
Okay.
Right.
So that's a bit different than this. We can use that null hypothesis to test to see whether there's a violation of these assumptions. So we'll get to that.
But it's still saying that there's no relationship
Yes.
for the outcome.
There, not the outcome. If we're saying homoscedasticity, no, autocorrelation or serial correlation, there is no relationship over time, right, with the errors. And we'll talk a little bit more about what that means, right? No independent variable is a perfect linear function of other explanatory variables. But we can address that as well, right? Exogeneity, meaning all independent variables are uncorrelated with the error. Okay, so it's saying that, say we predict something, and we have these variables that are predicting something, we're saying that these variables are uncorrelated to those things that we can't predict, right, to the error out there, right? This one, last one, right? The error term is normally distributed.
That's the one that gets violated.
Normally distributed. This is usually violated. And this is not a really big deal, okay? Actually, as I've stated in the note here, one or more of these assumptions are usually violated, right? And later on, we'll discuss how we address these violations when conducting policy evaluation using the statistical techniques that you'll be learning, okay? So again, these are the classical assumptions of OLS. It's the ideal. It's not usually the case that all of them hold. But statisticians kind of build their academic reputations on statistical tests to address the violations of these assumptions. So when I was learning statistics, and I learned statistics with really no context, right? We're not learning it to do a project. We're learning it, kind of the theoretical aspects of it, and it's like, so what difference does this make, right? I would always ask that question, why are we spending all this time about the assumptions of statistics and the violations of the assumptions? And it was years later when I started to apply statistics that I learned the importance of these, because they have implications. Once they're violated, they have implications for the methods that you use, okay? Okay, so this is a simple depiction of an OLS equation that you would see in a statistical text, where y hat is the expected outcome. Expected, say, enrollment, if you're looking at enrollment as an outcome. Beta subscript 0 is the expected average outcome of the predictor, whatever it is that you're using, say financial aid or whatever. Say it's 0. That basically is just the average of enrollment. Say you're looking at 50 states over 10 years, the average of enrollment, right? Okay. X1 is really a predictor, right? So again, if you're using financial aid as a predictor of enrollment, that's X1. The error term, remember we talked about the error? The error is really what's left over from the prediction. So you predict enrollment, say, for a given level of state need-based aid is, I don't know, 100,000. But your model says it's 75,000. So the error is the 25,000 that's left over, that it didn't predict, right? Again, you don't have to remember this. Squared errors, some of the squared errors, this is the equation. Again, y subscript I is the actual, and y hat subscript I is the expected, related to what I just talked about, right? That's the actual, that's the expected, what's left over, error, squared, okay? This is an OLS regression model with one independent variable. When I was learning statistics, even after I learned like the basics and I took a course in econometrics, which is really applied statistics to economics, we had to remember that equation. Okay? No one does that anymore. No one commits this to memory. The computer does this. The computer, the statistical program that you're using will estimate the beta hat 1, right? Which is the regression coefficient. So that's the value that it assigns to that predictor, right? And we'll talk a little bit more about that. Okay. Beta hat subscript 0, as I mentioned, that's based on averages, right? Average, that's the average outcome, that's the average of a predictor, right? This is the total sum of squares. So it's really what you have as the actual minus the average squared, right? And dividing that by n minus 1 gives you the sample variance. Remember we talked about variance? Looking at how it's dispersed around the mean, right? Okay. So why is all of this important to know? Because when we're using a regression model, we're trying to explain something, right? We're trying to explain the variance, really, to be more specific, of something. So how much does enrollment vary based on how much need-based aid varies, right? Or the variance. So there's a measure of that explanation by the model of that variance through this regression sum of squares, right? And this is the little formula that's used. Everyone follow so far? Okay. So when you run a regression model, it will give you the R squared. So it's the regression sum of squared divided by the total sum of squares. And it would also give you an adjusted R square, right? Which is this equation here. Again, you don't have to commit that to memory. And this R squared, the higher the R squared, the better the regression model, what we call, the phrase that we use, fits the data. The higher this R square and this adjusted R square, the better your model fits the data. Now, cross-sectional data usually have lower R squares than time series data. Why? Because there's more variance. Looking across 50 states for say, enrollment, you're going to have a lot of variance, right? Because what? Rhode Island and California, right? I heard someone say, should we even consider Rhode Island to be a state? Yes, it's a state. Someone also said, should we not have like the North and South Dakota become one state because, you know, there are like more cows than people in those states? So you hear all these jokes about states. I have it in the chat here. Satra, did you have a question that you put in the chat?
No, I have no questions. They're probably old.
Oh, okay. So in a time series, you usually have a higher R squared. Say you're looking at Maryland over time, one state over time. That's a time series. And you're looking at enrollment and you're saying, well, what determines enrollment in Maryland over time? You may say, well, we have this predictor. We call it, you know, merit-based data or need-based data, whatever you decide. That R square is going to be higher than looking at Maryland compared to other states using the same variable, right? Because there's less variance in that outcome and in that variable over time than there is looking across states, right? So that's why the R square for the time series is usually higher. But we're not really interested in the R square because we're not using our models to predict. We're using our models to find out the importance of a variable, a policy relevant variable. Or if we're looking at the effect of a specific policy on an outcome in one state compared to other states, we're looking at the statistical significance of that variable that measures or that operationalizes that policy, right? So don't pay too much attention to R squares. We don't pay too much attention to R squares in education research. But we should know what it is, right, when we see it. Standard error of an estimate. So this really means, well, to what extent we can't explain something, right? So this is kind of the flip side of the R square, so to speak, right? That's the standard error. And I should move this down so you can read the top. Okay, so as long as the assumption in slide 7 hold, the OLS estimator of multiple coefficients, multiple variables of a linear regression model is the best linear unbiased estimator, or BLUE. Has no political implications here. It's just what statisticians decided. This is digressing a bit, but I was reading over the weekend something totally unrelated to this class, and I found out that the blue and red designation of states is actually a creation of the media back in 2000. There was nothing in the political science literature referring to blue and red states. Just an aside. Okay, so for example, suppose we know the true model of the relationship between an outcome and an independent variable, say x1, as y equal 1. Here is the beta coefficient, beta subscript 0, right? When x is equal to 0. Say we know that the relationship between x1 and y is -2. meaning it's a negative relationship, right? And the value is 2. Okay? And we have some error. So we have this true value, we just know that that's the true relationship, okay? And E is the unobserved error, right? What we can't explain. So we have a model of probability based on normal probability distribution of X1 and E, going back to our slide 7. And we produce data through this data generating process that I talked about last time. We then use this DGP to create a data set of, say, 50 observations based on normal distribution of X1 and E. Okay? Everyone follow? Okay. Okay, I guess I have to go in here every time I do something. Okay, so in Stata, after we create this simulated data set, it's not real, we regress Y on X1. You would get this. That's an ANOVA table, analysis of variance. Don't worry about it. We don't use it. People who run regressions don't use it, right? So don't worry about that. But you do see certain things here, right? You see what? The R square, meaning 74% of the variance in Y is explained by X1. When we adjust for that, right, n minus 1, 73%, same thing. Okay, don't worry about the root mean square error. This is the beta coefficient here for X1, that beta subscript 1, right? That's it, right there. It's almost -2, but it's not quite -2. This is the purist, right? Mathematical purists would say it's not quite 2, right? It's -2, it's -961,863, right? It's statistically significant because the p-value is less than 0.05, right? But all you would do in Stata to get this is to type in reg, short for regression, y, x1. That's it, and you get this output. Simple. Okay. Now, I did this. I ran the same regression, y on x1, but I simulated a data set where we would randomly draw samples 1,000 times, okay? Notice how it increases to almost a true value. It's still, again, the purists would say, well, it's a little over, right? But it's much closer than the previous estimate, right? Or one could say it's equal to the true value, right? So what does this demonstrate?
More observations are better.
More observations are better, right? It also shows that OLS estimator is the blue, right? Specifically when the first 6 classical assumptions hold. So it's all assuming those assumptions hold, right? And down to the bottom, which you can't read all of it, but it's basically saying I use Stata to generate this data set via a Monte Carlo simulation. If you're interested, you can go to Elms. It's there. You can look at the code that I use for that, right? This is done for pedagogical purposes. We have the standard error. We have the p-value, right? Again, it's not 0, right? That's proof that it's not 0, even with 1,000 sample draws, right? Okay. And we reject a null. We rejected a null because 1 is not 0, so we rejected a null, right? Okay. Any questions about that? Okay. So now here is a depiction in a graph. right? This shows like enrollment here, need-based aid here in the millions. This is in thousands. This shows a positive relationship between enrollment and state need-based aid, which implies that for every million, right? And this was done in Excel. So that's why you see kind of, this is flipped, right? This is the beta subscript 0 here, and this is the beta subscript 1 here. For every $1 million increase in state need-based aid, undergraduate enrollment increases by what? Approximately 1.1. So this tells you two things. It tells you that there's a positive relationship, right, between need-based aid and enrollment, right? And it tells you what the value is here of the relationship. It's positive and it's 1 to 1, 1 million to 1,000. Okay? Now look at these little dots. Those represent, this is the line that's fit through those dots. And these little dots, the distance from that dot to that dot represents an error. So, you know, if it was perfect, that dot would be down here on the line, but it's not, right? So if you compute the difference between each of these dots and the line, and then you square it, you get what? The squared sum of errors, okay? Some are below and some are above. The reason why we square it is because we have to take into account the negative and the positive. And when you square it, it just comes out to be a positive, okay? But everyone see the relationship here, understand the concept? Okay. So now this is different. Is this a straight line? No.
No.
It's what we call curvilinear.
Curvilinear.
Curvilinear, there's a curve in the line. Curvilinear, right? And this is the equation that we would use for curvilinear. So we would have the x, but we also have the x squared. So when we use this, we can actually fit these data points and have the best fit for these data points, but it curves, okay? Sometimes the R square increases substantially. Sometimes it doesn't. I don't think it really did in this case, right? So remember the first assumption, it's, you know, we said it's linear. Well, what if it's not linear? It's okay, because we can put in an equation here that has the x square, and we could take into account this curvilinear, okay? But if you do that, you see what? It changes slightly here, right? This becomes 1.6. In the previous slide, it was just what?
1.1.
Yeah, 1.1. So there are implications for the model that you use with regard to the results that you get. But how would you know whether your data are linear or curvilinear? How would you know that ahead of time?
You can kind of plot it and take a look
Mm-hmm.
if it's obvious.
Mm-hmm. Yep. You don't have to do that and give me that plot. But if you find it, you can say, well, I did it, and the data is best fit with a curvilinear line versus a linear line. Okay. So plotting it, it's easy to do it in Stata. You can actually plot your data. Okay. I plotted data looking at net tuition revenue per FTE And the relationship between that and state appropriations per FTE, it's negative, a negative relationship, right? Downward sloping, so it's negative, right? One could say it's linear. But it could be curvilinear. Again, I did this in Stata, right? Any questions about this? This is particularly the case when you're looking at a correlational model or using a correlational model, right? So those of you who are using that correlational model might want to check on the variables, on the data that you're using to see whether they're linear.
Can I ask a quick question? Would my research be a correlational?
No, it wouldn't. You're doing a causal inference. You're looking at a specific policy, right? Oregon Promise program, both you and Younger. Yeah, so typically no, you wouldn't look at this. Okay. Just some humor here, right? I don't trust linear regressions when it's harder to guess the direction of correlation from constellations. Okay. Okay.
What we would call that constellation?
I'm sorry?
I said, I wonder what we would call that constellation. Man carrying Martini.
I guess. I guess. I guess. Okay. So let's look at a Stata output. Actually, we just looked at one, right? From a bivariate OLS regression, we have the beta. And Stata doesn't say it's beta coefficient, but it's really the beta coefficient here. It just says coefficient. This would be the beta 1, right? The value of the beta 1. This would be your x1, or x, your independent variable. This would be your y variable, right? Your outcome variable. So typically, this is what you would see from a Stata output, utilizing regression, OLS regression with one independent variable, right? Okay. Or if you wanted to put in or look at a curvilinear, you would put this in, right? You would put, because this here being state appropriations FTE, being a continuous variable, you would put C period, the variable name, and then a hash mark, and then a C period, the variable name again, and it would give you the beta subscript 2, which is that x squared, right, that we talked about earlier. And that would give you the value. Notice this is negative, but this is positive, right? So you get that curve. Negative, 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 then an inflection point, and then going up, right? Here. So any questions about this?
So, just using this table, how do we interpret the p-values? Because they've always been 0.
Mm-hmm.
And I know it's based on something to do with t, so like, how would we determine statistical significance?
So as soon as you see that p-value equal to 0, which, as I said before, Stata does that, but it's not really 0.
Okay, so it's not actually 0, and we're not looking at the t-values at all. That's sort of
Yeah, you could look at the t-values, but the key statistic to look at is the p-value, right? So when you write up your paper, you would put, p-value less than 0.001,
Right, okay.
right? Because remember when we ran that 1,000 draw simulation,
Right,
it
right,
was
right.
still,
Yeah, just like to the negative.
right,
23rd,
you're right, it was still not 0, right? And you know, I tried just for fun to run it like 10,000 draws to see how far down it goes, but it'll never get to 0, I don't think. Okay, so any questions about this? How much time do I have here? Okay, let's keep going for another 10 minutes. Okay, so from the previous example, and this is where we get more into the null. We could reject the null hypothesis that the beta coefficient B1 is not equal to 0, or accept the alternative hypothesis that, what? Beta 1 is not equal to 0, right? So beta 1 is equal to 0 is the null. Accepting the alternative is not equal to 0 when we reject the null, okay? So we can use this hypothesis testing with OLS regression. To do this, we have to find, remember the standard error of the estimate or the parameter? Well, this is the standard error of the parameter. Again, you don't have to remember this, okay? But the higher this standard error, the less likely you are to reject the null. Okay. And the smaller the standard error, the larger the t. And the more likely the probability that the null will be rejected. And we can make the claim that the parameter is statistically significant. Okay? If we reject the null with more than 95% certainty, 95% of the values of beta lie between plus or minus 1.96 standard deviations, then we can say B, or beta, is not equal to 0, or not the result of statistical chance, right? So what we're saying is whatever result we get, we reject the null, we're saying that result is not due to statistical chance. This is the same thing as saying that there is less than a 5% probability. Remember this, P, remember what I talked about? P value being less than 0.05. There is less than a 5% probability that the estimated coefficient is equal to 0, less than a 5% chance. Now, when we have that p-value is less than 0.001, we're saying it's what? It's less than a what? 0.01% chance, right? So the lower this is, the better, that p-value. If the p-value is greater than 0.05, then it's not acceptable and we cannot reject the null hypothesis. That's why standard errors are very important. The standard error, the betas, are very important. So what are those? These things here. Standard error. That's the standard error. The higher standard error, the lower the t-value, the lower the t-value, the lower. This should tell you something here with regard to the probability of rejection. Okay?